start recording this time. So we've got with our dival here, diethyl hydride, and dival converts things to aldehydes. So anytime you have an aldehyde, except as the product from an acid chloride, it's probably going to be dival. So we just need to make sure we get the right number of carbons. So it goes through the imine with the aluminum attached to nitrogen, and then aqueous acid hydrolysis converts that imine to the aldehyde. This is an ester being converted to a primary alcohol. That's being reduced all the way. So that's lithium aluminum hydride, and you can use either ether or THF. Doesn't really matter which. And an aqueous acid work will protonate the alkoxide that results from the initial, it's a nucleophilic acyl substitution to kick off the methoxide leaving group, and then that aldehyde is reactive nucleophilic acyl addition to form the alkoxide, which then gets protonated. This one is a reductive amination. We've got an acid catalyst and an amine, which is going to convert the carbonyl group, the ketone in this case, to the iminium salt, and then the iminium salt is what gets intercepted by this hydride reducing agent. The product becomes the amine. And in this case, we have a CH3 group attached to the nitrogen, and we also have a CH3 group attached to the carbon. So that's a reductive amination. Lithium aluminum hydride, as opposed to dival, it's the same substrate here, it's the nitrile, but lithium aluminum hydride will reduce the nitrile all the way to the amine instead of stopping at the aldehyde stage. And you just have to be careful to make sure you don't lose a carbon. So you have 4 carbons in your main chain with the amine attached. Here we have the same acid chloride. We're converting it to a ketone in the top reaction and then to an aldehyde in the second one. The way to convert acid chloride to ketones is to use cuprates. In this case, butyl cuprate, because we've got the butyl group on there, so C4H9, 2Cu-Li in some inert solvent, CHF this time, and then the aqueous acid workup. You'll notice that with the exception of the acid to the acid chloride and the reductive amination, all of these have an acid workup. To convert the acid chloride to the aldehyde, we use lithium tributyl, aluminum hydride. So we've got those electron withdrawing groups on the aluminum to make it less reactive. So we do that in some inert solvent. And then aqueous acid workup again. All of these aluminum and boron reducing agents are going to have that. Here we have an ester. We're treating it with excess phenylmagnesium bromide, which I guess didn't have a D in it on the quiz. Sorry about that. So we want to make sure we don't lose any carbons. That's a 7-carbon chain, and then on carbon 1, we're going to attach 2 phenyl groups and make a tertiary alcohol. So the intermediate is ketone. But that ketone will react with another equivalent of phenylmagnesium bromide to form the symmetrical tertiary alcohol, where we've got 2 phenyl groups attached. I skipped 6. It's actually 6 carbons, not 7. I can't count today. Amide being converted to an amine, that's reduction all the way. That's lithium aluminum hydride reduction. It's pretty much the same reaction as this one, where the nitrile is converted to the amine, amide is converted to the amine. Any of the functional groups that have the nitrogen in them get reduced to the amine rather than to the alcohol. The acid chloride, the hydride, the ester, and the carboxylic acid itself get reduced by working along the hydride to the alcohol. Got an ester, we're trying to get an aldehyde. The aldehyde product is a result of a diol reduction, so amates, nitriles, and esters all generate aldehydes with diol, ether CHF, followed by this acid workup. And then this one, which I actually skipped, I think it was here, it was number 7, is the carboxylic acid going to the acid chloride, SOCl2. Or in fact, you could use PCl3. SOCl2 is the more common source of chlorine for acid chlorides, and PBr3 is the more common source of bromine for acid bromide. But you could use SOBr2 to make bromides, and you could use PCl3 to make chlorides. Both of those are acid chlorides of a acid that's more reactive than the acid chloride, the carbon acid chloride that you're making. So either of those two reagents will do. They're both liquids. They're both easy to work with as long as you work under an atmosphere that doesn't have water in them. So that's the quiz. And I'm going to save this video separately.